new business opportunities, etc. Sir also looks after key account management of few air conditioning customers. Mr. Rahul Pathak is a mechanical engineer from Government Engineering College, Aurangabad, and MBA in marketing from Pune University. Sir has a total work experience of 12 plus years in marketing and business development. Sir began his career
You're not audible.
Hello, Chaudhary sir. You are not audible. Hello. Hello. Pathak sir, let's see.
All right, can we start?
Just second, sir. Just second.
Yeah.
Hello. Pathak sir.
Yes, sir.
Sir, please you continue.
All right. Okay. Okay. Can you see my screen? Am I audible enough?
Yes, sir. Yes.
All right. Okay. So, welcome all of you, and thank you, Pimpri Chinchwad College of Engineering, Pune, for giving me an opportunity to interact with all of you on a completely different subject, because we often talk about Emerson product range, how it is better, and what is the value story, all of that. But this is kind of a neutral topic, where I will take you through refrigerants, the market scenario on the refrigerants, and scroll technology. What is new into the scroll technology, along with the basics of the scrolls. So, so whatever knowledge I have gained so far in HVAC and R on in these two areas, I will try to kind of share. I don't call myself as expert, but whatever information I have so far, I'll try to share with all of you through this session. So thank you once again, and we will start this session. So this is our today's agenda. So refrigerant landscape, that's our starting point, followed by the phase down schedule of these zero ODP and low GWP refrigerant. So we'll talk about that. Followed by the search of the alternate refrigerant. This is going to be our main topic, and also basics of the scroll technology. And towards the flag end of this presentation, we'll quickly go through the variable speed technology in scrolls. Okay, some basics of the inverter drives, right? How it works. It is more on the electrical front, but let's see how it functions. And then the last point would be maybe it may be relatively new to the participant, but I'll try to share this economized vapor injection technology in scrolled compressor, how it helps, and what are the features of this technology as far as the systems are concerned. So all of that. So this is our today's agenda for next almost 1 hour, and I'll try to kind of abide with this timeline that I've set. All right. So let's speak about the two points. One is the refrigerant landscape and the phase down schedule. So this is kind of a very busy chart. Let me try to explain this and simplify it for all of our participants. The x-axis is the GWP, or the global warming potential level of a refrigerant, and the y-axis about the pressure of the refrigerant. Okay. Now, if you see on the right-hand side, today the India air conditioning industry is hovering around the use of R22 and R407C, and slowly kind of moving to the zero ODP refrigerant option like 410A. Right. So the movement is on from R22 oblique 407C to R410A refrigerant. So that's the today's movement. But is it sufficient enough for India to comply with the commitments towards like Kigali Agreement or Montreal Protocol? The answer is no, because this addresses only the Montreal Protocol commitments of India, right? What Montreal Protocol says is you have to move away from high ODP refrigerant to zero ODP refrigerant, which we are doing right now. But at the same time, we also have to take into consideration the GWP level of refrigerant. ODP is not sufficient enough for India. Okay? So one point we have addressed by moving towards a zero ODP refrigerant, but at the same time, we are deteriorating the use of refrigerant with high GWP level. Remember, I said the x-axis talks about the GWP level. Okay, so 410A has a is a zero ODP refrigerant, and at the same time it has a high GWP. Our ultimate goal is to see how do we kind of travel from right hand side to the left hand side of this graph. Okay, so what options we have, and that's our main topic today. What options we have, so we will evaluate few alternate refrigerant compared to 410A and see what best suits for us, what best suits for Asian countries, what best suits for the developing countries or the developed countries like US and UK. So let's brainstorm around those points. So as I said earlier, so our short-term game is to move away from 410A to a mid-level kind of a GWP level refrigerant, and then ultimate aim is to find out what refrigerant we have in our hand which has GWP level of less than 150. It's very hard, but industry is trying hard to kind of get a right solution for the air conditioning and refrigeration industry in coming years, right? So if you see towards the mid size of this chart, the mid level of the chart, as we travel from right hand side to left hand side, the short term refrigerant option right now is R32, which has GWP level of close to 675, okay, which is far better than 410A. And then if we travel from this point towards the extreme left, we have few options like ammonia, R290, 1234YF, or maybe CO2. Now, these are extremely good in terms of the GWP level, but at the same time, their parameters are not good enough, or the properties are not good enough to straight away use these refrigerant in any of the applications, because one has to take care of other properties, like for example, CO2 is extremely high pressure refrigerant, right? So the system cost goes up if you try to use the CO2 in a primary circuit. So even from the reliability point of view, it's relatively dangerous compared to the refrigerant that we use today. So people are in the developed countries trying to use this refrigerant in the secondary loop, but at the moment you use in the secondary loop, the efficiency goes down, right? For example, ammonia, it's toxic in nature. So you can't use ammonia in a municipal limitation of any city because it's toxic in nature. So it has some disadvantage of to some extent in terms of the property, right? R290 is extremely flammable. Can't use this beyond a certain charge limit and air conditioning applications. So there are some instances in India where R290 is getting used in room air conditioners, but not beyond that, because the limitation on the refrigerant charge limit of R290 in air conditioning system, right? So all of that. So the point is, the takeaway is we have to move from right hand side to left hand side. At the same time, we also have to take care of the refrigerant properties and make a decision what refrigerant is suitable for Indian industry going forward, right? So that's a complete refrigerant landscape in front of us as far as the Indian industry is concerned. So with this background, let's move towards the phase down schedule for India, okay, as far as the refrigerant is concerned. So there are two main protocols which India has to abide. The first protocol is the Montreal Protocol. Montreal Protocol talks about the ODP level of the refrigerant. It says that the country should use the zero ODP refrigerant. ODP is the ozone depletion potential, which has a zero ozone depletion potential. That refrigerant should be used. That's what the Montreal Protocol says, and we are committed for India is committed for the Montreal Protocol, right? So as per the protocol, the timeline is this, and how it is calculated, I'll explain this now. Whatever consumption we had for the HCFC, which is like, for example, R22, it's not a zero ODP refrigerant, right? So we have to get rid of this refrigerant by phasing down, right? So what timeline we have is the consumption we had of R20. So whatever R22 consumption India had in 2009 and 10. At the same time, whatever production we had of R22 in 2009 and 10. So these values have been given in tons. If you take the average of these baseline, so that's the freezing point for us. So that much amount of refrigerant or R22 refrigerant has been freezed in 2030. So we were not allowed to use that much amount of R22 refrigerant in 2013 and beyond. Okay? So that was the freezing point for us in 2013. 2015 onwards, so we have started reducing or phasing down the freezed amount by certain percentage. So in 2015, we reduced it by 10%. In 2020, in Jan 2020, we have reduced it by 35%. We are expected to reduce it by 67.5% in 2021. And by 2013, R22 will be completely phased out from India. So that's the timeline we have as far as the use of R22 or the use of HCFC in India. So there is one more agreement which we are abide. India is abide. Government of India has given a commitment from the environment point of view, and that agreement is the Kigali Agreement. Now, this is nothing but small amendments in the Montreal Protocol. Okay. Now, what that amendment is, now the Kigali Agreement says while ODP is important, at the same time, the GWP level of refrigerant is also important. So it says or it recommends or the countries who are abide to this Kigali Agreement is expected to phase down the use of refrigerants having high GWP, okay, or high GWP level. So there are different categories because it's not easy to find out an alternate to the HFC refrigerant like 410. It's not easy. So based on the economic condition, there are different groups formed in the Kigali Agreement. For example, for the developed countries like US and UK, they have already started phasing down the HFC refrigerant in their country, right? 10%, 40% in 2024, and by 36, they're expected to reduce to 95%. Whereas in the developing countries, again, there are subgroups. Like in group one, like China, a little relatively developed country, the starting year for freezing the HFC refrigerant is 2024, and by 29 they will start phasing down this HFC refrigerant. As far as India is concerned, we fall under group 2 countries, and the freeze level or the freeze year would be 2028 and not 24 for as far as China is concerned. For China is 24, but for India is 28. And then you can see from 32 onward, we'll start phasing down the HFC or the R410A refrigerant. Try to see what refrigerant option we have to replace the R410A or 407C or 134A kind of HFC refrigerant that we currently use in India. Okay, so that's the refrigerant schedule for us. Now let's see what alternate options we have to replace the 410A refrigerant, which is a very high GWP. Okay. Now, before we go ahead, let me explain this TEWI term, which is Total Equivalent Warming Index term. Now, it's a combination of direct global warming and indirect global warming potential. What we spoke just now is only on the direct global warming, because what we believe is direct global warming, which is a cause of refrigerant leakage of a particular refrigerant. Now, when we say a particular refrigerant has a high GWP level, that means if it leaks, it has a potential to affect the global warming of an environment, right? But only if it leaks. But that this problem is only the 10% of the total problem. The real problem is the indirect global warming, right? That means it has a connection to how much energy efficient that refrigerant is compared to the other refrigerant. That contributes to around 80 to 90% of the problem. So it's just not what GWP level of refrigerant is, but at the same time, we also have to take into consideration how energy efficient that refrigerant is to reduce the indirect global warming. I'll give an example like what indirect global warming means, right? So if you use a refrigerant which has a low GWP or the direct GWP level, but at the same time it is not energy efficient, and if you try to use that, you are calling more energy, more power from your power station, right? And at the same time, if you use the less energy efficient refrigerant, you are consuming more power, you are demanding more power, so you are consuming more coal to generate that electricity, right? So ultimately, you are affecting the global warming of an environment, right? So if you combine the direct global warming and the indirect global warming, the term is called TEWI, which is Total Equivalent Warming Index, or we also call it as a LCCP, which is Life Cycle Climate Performance, right? So TEWI or LCCP should be a term to evaluate a particular refrigerant. Okay, that's the message I wanted to give to all of you. So this is a direct global warming potential values, just for your information. Like, for example, the R22 refrigerant that we use, I said earlier, it's not a 0 dB refrigerant. It's The ODP level is 0.05, very harmful for. So that's the reason, because of the Montreal Protocol, we are expected to move away from R22 to refrigerant having zero ODP. That's a commitment for the Montreal Protocol. But is it something we want to achieve ultimately? No. We also have to take into consideration GWP level of the refrigerant. So right now we evaluated 410 as an alternate to R22 to address the Montreal Protocol. But by addressing this, the problem is the 410 has high GWP level of 2088. So though it's a short-term solution for us, we have to see what alternate option we have in HFC refrigerant family, which has a relatively lower GWP level. So if you go down to the list, there are options available having a low GWP refrigerant. Right? So let's see how do we kind of evaluate these refrigerant options. So before we move ahead, this is a safety classification chart. How a particular refrigerant is classified based on two parameters. The class A and class B, class 1, class 2, and class 3. So if you make a matrix of class A, class B versus class 1, class 2, and class 3, all of your refrigerants fall into any of these boxes, right? Now, class A defines that this is a non-toxic refrigerant. Class B means it's a toxic refrigerant. Whereas class 1, class 2, class 3, class 1 defines that it is a non-flammable refrigerant. Class 2 defines it's a it's a mildly flammable refrigerant. Class 3 defines it's extremely flammable refrigerant. Right? So if you try to make a matrix, all of your refrigerant falls in any of these boxes. Okay? So remember, this is very important chart when we move ahead and try to explain the alternates available to the 410 error. Okay? Just wanted to kind of check with one of you if I'm audible enough and the charts are visible. Can you confirm?
Yes, sir. You are audible.
Okay, thank you so much. Okay, so let's move to the next chart. Please mute your phone on our WebEx. I'm hearing the echo, so okay, all right. I think yeah, I can mute it now. All right, so let's see how do we kind of find out an alternate refrigerant for the 410. Now this is called the radar chart. Okay, now those who are not familiar with the radar chart, let me explain how we kind of read the radar chart. Now radar chart is in the circular format, okay, having one center, and all the properties which we want to evaluate are situated on the periphery of this circle, right? And when we evaluate a particular parameter and locate these parameters, then if the location of those parameters are on the periphery of the circle, that means that property is a good property. Okay. If the location of these parameters is towards the center, right, of the circle, that means that parameter is not a good property to evaluate, or it's not a good property from the use of that particular reference, right? So remember, if the parameter is on the periphery of the circle, if the location of the parameter is on the periphery of the circle, that is positive point, it's a good point. If the location of the parameter is towards the center of the circle, that means it's not a good property to have. Okay. So with this basic understanding, let's now evaluate. Now, for the comparison, purpose, we need to have some baseline. So let's take 410 as a baseline. Now, if you see 410 as a baseline, see all the properties. Now, what those properties are? the properties are divided into three sections. The properties having an impact on the compressor, like the compressor capacity, the compressor efficiency, right? So it has a connection to the compressor or the impact on the compressor. Second is the system impact, whether it's a glide or the compressor and system cost or the heat transfer pressure drop. These are the properties related to the system. And the rest of the properties, like flammability or GWP level or the toxicity, it has an impact on the environment, right? So these properties are divided into three sections. Now, if you see 410A, which is a base refrigerant, and then then we will evaluate rest of the options related to 410A. Now, 410, if you see and try to evaluate 410 as a refrigerant, look at all the properties having location on the periphery of this chart, whether it's the compressor capacity, efficiency, toxicity, flammability, heat transfer pressure drop, glide. All of those properties are good. We do not have any issue as far as these properties. But if you look at the GWP level of 410, the point E or the location is shifting towards the center of the sun. Okay, that means this is a negative point. It's not a good point to have. Okay, because remember, if you see earlier chart, 410 has a GWP level of 2088. That means the point is shifting towards the center of the radar chart, right? This is how we will evaluate other options with the base as a 410 reference. Okay? So what options we have to 410? First option is R290, which is we all know, it's a propane refrigerant gas. It has a low GWP level, the availability is good, efficiency is good. It's kind of a very similar pressure as compared to R22. So one did not have to worry about the system design changes in air conditioning. But the point is, it's extremely flammable because it has a low volume limit, high flame velocity, low ignition energy. All of these are basic terminology. You can go through these terminologies later on. Because of the paucity of time, I may not be able to explain this terminology because a lot of things we need to cover in the limited span of time. So, but with these, if you want to kind of get rid of this flammability issue, one still can use this R290 refrigerant in a secondary loop. But if you try to use this in the secondary loop, like Europe is doing, your efficiency will go down by 10%. So, and as I said earlier also, the charge limit is only 300 grams. So if you go beyond this, the flammability is a concern for your air conditioning system. Let's try to locate this R290 in our radar chart and try to compare with our baseline of R410 refrigerant. So red line denotes is a R290 refrigerant. So look at all the parameters: glide, heat transfer, compressor capacity, efficiency, compressor efficiency, toxicity, GWP, all are good. We don't have any problem in any of these parameters. But look at the flammability. It's the point is shifting towards almost close to the center of the radar chart. So it's extremely dangerous. Okay, so flammability is something which is bringing down the probability of using as an alternate to 410A. So the point is, the takeaway is, you cannot use R290 because of the high flammability rate, nature of this refrigerant. Okay. Now let's see the next refrigerant option. The next refrigerant option is R32. Now R32 is a part of your 410. If you see the 410A property, 410 is a blend. It's a blend of 50% R125 and 50% R32. That's the blend of R410. 410 is a combination of R32 and R125. So coming back to R32, it has a relatively low GWP of 675. Availability is good. It's efficient. slightly better than 410A. Pressures are slightly higher than 410A, so but that's manageable. But it's mildly flammable. Okay, it has a low burning velocity of 6.7 centimeter, much lower than the R290. High minimum ignite energy of 30 to 100 energy of to ignite that particular refrigerant. And the problem, one more problem associated with R32 is the discharge temperature is relatively high. So when you use this R32 refrigerant, one has to control the discharge temperature of R32 in a compressor by injecting vapor or by injecting the liquid refrigerant inside the scroll set to control the discharge temperature of R32. So let's look at how it performs on our radar chart. This is a R32 refrigerant compared to 410A, denoted in blue color. So all of these properties are good, from heat transfer to glide to compressor capacity, cost, efficiency, toxicity, all they are good. As far as GWP is concerned, it's not extremely inclined towards the center, but it is somewhere closer to the periphery of the center. So though it's not that dangerous, but it's matter of concern. But with some care, we can handle this particular property of GWP. And then flammability, it's again not inclined towards the epicenter, but it is again falling very close to the periphery. So it's not that harmful, but as I said it earlier, it's a mildly flammable refrigerant. Had it been flammable refrigerant, it would have been towards the center. But since it's a mildly flammable, with some care, we can handle that mild flammability characteristic of R32 system. Right? So that's how it scores on the radar compared to the 410. So with this, I'm not going to kind of talk about each and every refrigerant, but if you add few more refrigerants like CO2, like 1234 YF, right, and try to compare with 410A, this is how your radar chart looks like. For example, CO2, so all the parameters you see are good, but when it comes to the compressor efficiency, and it comes to the compressor and the system cost, because as I said earlier, the pressures are very high in CO2. So when you design a system with a CO2 refrigerant, the designer has to put a lot of material cost into the system to handle the high pressure refrigerant. So when it comes to the system cost or the compressor cost, the point is shifting towards the center of the radar chart. Even the efficiency, when you try to use in the secondary loop, it goes down. So efficiency wise, it's not that good. So likewise, if you try to evaluate 1234 YF refrigerant, which is denoted in the orange color, it's not that good. Whether it's a flammability, whether it's a compressor and system cost, it's not that good. Even the pressure, heat transfer pressure drop is also not good for the 1234 YF. So what it denotes, we are still not kind of not being able to find out a perfect alternate to your benchmark or the baseline of R410 refrigerant. But we are kind of very close to find out an alternate to 410, and that is R32. It's not I would say a perfect alternate, but it is close enough to replace R32 to some extent as a short-term possibility, right? And that's what the industry is looking for as a short-term strategy to replace 410A and use 32 and trying to reduce the GWP refrigerant in a lot of countries. So If you see this chart in a different format, the said 410A is your baseline. And if you try to see the efficiency, the system efficiency level with 410 as a baseline, your R290 efficiency level goes down by 0.9 index. Try to use in the secondary loop. If you try to use R290 straight away in the primary loop, it is kind of matches the 410 refrigerant system efficiency level. In the CO2 refrigerant, the system efficiency index goes down by almost 0.8687. But look at R32, it is slightly ahead than 410A as far as the efficiency index is concerned. And with though it's a A2L flammable category refrigerant, but with some amount of protection, you can get rid of that particular property. But look at the efficiency index. It is more than 410A, which no other refrigerant has any property which has an efficiency index greater than 410A. And look at other refrigerant like 134A and 404A. Right? So they have the efficiency index less than 410A. So that's what I want to do. Communicate that R32 is something coming out as a short-term strategy for industry as an alternative to 410A. So remember, the LCCP or TEWI concept, which I explained earlier. R32 not only has a relatively lesser GWP, but since it has a efficiency index greater than 410A, it can help us to reduce the indirect global warming potential of the system. So your LCCP or TEWI index can go up. R32 refrigerant. So if you see this matrix of refrigerant evaluation, you will see different refrigerant being evaluated on different parameters. So the red star denotes these are not good properties. Green stars denotes these are good properties to have, and the semi or the semi-green properties denotes it's good to have properties, right? So if you see this particular evaluation matrix, refrigerant having a large number of red stars, are ruled out as an alternate. But if you see the R32 having a large number of green stars, clearly comes out as a short-term alternate refrigerant, whether it's an environment protection or safety or technology or performance or investment cost. R32 evaluation is on a positive side compared to the rest of the refrigerants. If you see room AC, currently we are with R22 and 410A, and a lot of room ACs are now, you might have found in the market with R32 refrigerant. I would say it's R22, 410A, and now with R32. Like cassette AC, vertical, and those kind of applications are with R22. But now also they are moving fast towards 410 and 32. Precision AC, 407C is the current trend. 407 is the current trend, and they are likely to move to 410A as well as maybe towards 4 or 5 years down the line. Who knows, 32 be a right choice for precision AC. Right now, they're currently being migrated towards 410A. Likewise, you can see the scroll chillers, 22 407C current trend, and they will move towards the 410A as an alternate option. R32 is also one of the strong candidates to replace 410A even in scroll chillers. Right? So that's what the trends looks like as far as the use of refrigerant in different applications. With that large session on the search of alternate refrigerant, we are done with the phase one of our today's presentation. We will move to the second phase or the second topic of today's presentation, and that's on the scroll technology. Before I move on, I think since most of us are from the academic background, I did not have to explain this vapor compression cycle, denoted in the pH diagram. So, but just to brush up, evaporation cycle. This is superheating. Then the vapor is compressed in the compressor. Then the desuperheating happens, right? Then the condensation starts, right? And then with the expansion valve or the capillary tube, you expand that refrigerant. Your pressure goes down suddenly, and here you get low pressure, low temperature gas, and then in the evaporator you start extracting the heat from the space, and then the evaporation starts. So very simple. All of us are familiar with this vapor compression cycle chart. The point is, in the overall cycle, the heart of this system is compressor. Right? So we will try to understand the scroll technology in detail and how it benefits, in terms of delivering the function of the compressor in the vapor compression. Now, one more point is in the COP level and the EPR level of the compressor is, as you know, it's a cooling capacity divided by the power consumption. Power consumption goes down from the compressor side, your COP. So it is extremely important for us to give utmost importance to use a higher efficient compressor in your system to improve your system COP. So compressor classification. So large scale, it is divided into positive displacement and the dynamic category. Positive displacement, it is divided into reciprocating compressor and rotary compressor. In reciprocating, you see single acting, double acting, and diaphragm kind of a compressor. In rotary, you have a lot of options like vane kind of options being used in the rotary, or the low kind of a rotary compressor, and we have scroll compressor, liquid ring, and screw compressors. Whereas in dynamic, you have centrifugal and axial. So centrifugal is largely used in the chiller application. Scroll is used in light commercial chiller application. Screw is again used in the large chiller application, like from 40 ton to 500 ton, whereas scroll is used in right from 1.5 ton, 2 ton to as high as around 30, 40 ton, right? So let's start now how the scroll compressor pass, because we are here to understand the scroll technology in detail. So let's see how it works. Now this is a small animation of a scroll compressor. Now this is a suction side of the compressor. So refrigerant is coming from the evaporator in the vapor form. It revolves around the motor side, it goes into the scroll side, and then compression happens over here, and the high discharge gas is comes in the discharge plenum of the compressor and it goes toward the condenser side to the discharge port. So this is how the compression happens. Small animation for all of us to understand how compression happens. Now this is the compression area where you have scroll sets. This portion is the fixed scroll set, and this section is the orbiting scroll set. Okay, and this orbiting scroll set is fitted towards the crankshaft, and then crankshaft is fitted on the rotor of the motor. So this is how the scroll set moves in the orbiting motion. So how this scroll sets looks like? So this is the fixed scroll. It doesn't move, right? It is attached to the main bearing housing of the scroll set. And this is the orbiting scroll fitted with the crankshaft and the motor of the compressor. Orbiting scroll meshes with the fixed scroll, and with the orbiting motion, we get the compressed gas inside the pockets of these flanks. Right? Now, how it really happens, let's try to understand it. When these two scroll sets mesh with each other, this is how the compression, I would say, pocket forms. So this is the outermost pockets. The refrigerant enters into the scroll sets, and the orbiting motion happens. So as the refrigerant flow towards the center of the orbiting, the volume goes down, the pressure goes up. And likewise, at the end of cycle 6, you get high refrigerant gas at the center of these four states, right? So pockets of compression happens from 1, 2, 3. Gradually, the refrigerant flows towards the center, and at the center, you get the high refrigerant gas. There are different technologies even in the scroll compressor category. We have something called compliance, axial compliance, and radial compliance. Radial compliance is associated with the moment of the scroll set on the axis. Okay, so to see the moment of this axial compliance scroll set, you can see this fixed scroll and the floating seal over here. So if you remove the floating seal from the fixed scroll, this is how your fixed scroll looks like with the intermediate cavity over here, right? So when the orbiting motion starts, the refrigerant comes from this intermediate cavity, which um, pressurize the refrigerant from the bottom of this floating seal, and then floating seal floats between this space and the discharge plenum of compressor, right? So it always floats. Now, the idea is, when these scroll sets meshes with each other, one has to hold these two scroll sets with the right amount of force. If you hold this scroll too tightly, then with the frictional loss, your COP can go up. But at the same time, if you hold these scroll sets with too lightly, then the refrigerant can leak back, or the high pressure refrigerant can leak back through these scroll tips back to the suction portion of the compressor. So care should be taken to make sure the right amount of force is holding these scroll sets, and that right amount of force is achieved through the floating seal. Now, this right amount of force can vary as the ambient temperature changes. If the ambient goes up, the amount of force inside the scroll set goes up. If the ambient goes down, the right amount of force inside the scroll set will go down. So it all depends upon at what ambient condition you are operating your scroll compressor and air conditioning compressor. So that's what the axial compliance talks about. Now, radial compliance. Now, radial compliance is the movement of this scroll set in the y-axis direction. If some debris or some liquid refrigerant comes inside the scroll set, the scroll can separate sideways in this direction, so that debris can easily pass without damaging the scroll sets out of the scroll compressor. And this can be achieved to unload a spring indicator. So this is called as a radial compliance. Now this scroll compressor, now this is about how this compressor happens or the compression happens in this. Now these are some of the applications where scroll compressors are used. Package air conditioners, precision AC, DRF, scroll chiller, process scroll chiller or the comfort scroll chiller, whether it's a VRF, all of these applications use the used in the commercial air conditioning. Now, whether it's a cold chain application, whether it's a food or processing plant, like there's cold rooms, refrigerated logistics, or continuous high applications which falls under cold chain market to make use of these for their end application. Right? Compressor manufacturer, we supply these scroll compressors in OEMs like you can see. I don't any of these OEMs, but you can see those OEMs on the chart. These are all. These are some of the examples who actually build these applications of these scroll compressors inside the application. Some of the buyers of the compressors who their application. With this basics of the scroll technology, I will move towards the last two sections, and that point is variable speed in scrolls, right? Now, so I have only two charts, I guess, charts which covers up the basics of the variable speed or the inverter compressor, right? I'm sure many of you might have studied this in detail, but I still would like to kind of brush up this particular basics of the inverter in a variable speed. Now, if you are trying to use a variable speed or an inverter compressor, you need to use a drive. Without drive, you cannot operate your variable speed compressor. Right? So what this drive offers to the compressors and the overall system? Right? So let's try to understand. Now, drive is used for various functions. One is to power your variable speed or the inverter compressor at point 1. The second is to get the controlling signal from your control board to RS485 Modbus. Accepting those signal and then varying the frequency and the voltage of the compressor is second job of your drive. And third is protecting your compressors. A lot of protecting devices are fitted on the drive itself. So that protection devices or the protection to the compressor is given to the drive, right? That's the third major function of the drive. Now, if you open this drive and see what are the internal components and components of the drive, let's try to understand. Now, when you give AC supply to the drive, right? Drive converts this AC supply to the DC supply. The reason is you cannot correlate the air conditioner or the AC supply with the desired frequency, because variable speed compressor is expected to run in the range of say 20 hertz to 120 hertz, right? So you cannot alter the frequency of AC supply directly. So you have to convert this AC into DC. And then you can actually modulate that frequency of the power supply by in the DC bus, right? Of course, there are IGBTs. We'll talk about it later on. So the first job is to convert the AC supply into DC supply, right? So that is that happens in the converter portion of your drive. So the diode bridge you can see. With the help of the diode bridge, you convert this AC into DC. But this is not a smooth AC. You have to convert that smooth, convert this into the smooth DC by the use of the capacitor or the smoothing capacitor. So that is the converter part of your inverter drive. Okay. Then you comes into the DC bus, okay, and then this DC is supplied to the inverter portion of your drive. Now, based on the signal through RS485 from the controller board, it says from the depending upon the cooling load. Let's say, for example, it says or it gives the order to the drive that your compressor should run at 40 hertz, not at 50 hertz, or not at 60 hertz. So based on that, inverter part decides based on this is called the IGBT part, having a lot of electronic switches, right? So based on the inputs received from the control board, the speed of the on and off function of these electronic switches converts the DC supply to AC supply. At the same time, it also converts the frequency of your AC supply. So the inverter portion does two things. One is convert DC into AC. At the same time, change the frequency to the desired limit. Right? So that's what the IGBT does by the use of the electronic switches, right? Now, remember in the electrical section, we might have learned in our electrical engineering that doing so, your V by F ratios should remain same in any motor, right? So if you change the frequency from say 50 hertz, say or 40 hertz, proportionally your voltage also will go down. Or if you change the frequency from say 50 hertz to say 90 hertz, proportionally your voltage also will go up to maintain the V by F ratio constant. Right? So that calculation happens in the inverter section, and then finally, this modulated air conditioning or AC supply is given to your inverter compressor. So that's how your inverter compressor is modulated, right? Of course, the motor used in the inverter section is not a standard induction motor. It is a brushless permanent magnet motor having a higher efficiency compared to the normal induction or the standard induction. And that's the reason we say the variable speed of the inverter compressors are highly energy efficient compressor compared to the standard ones, right? So this is a component for the single three-phase drive. Apart from the drive, one has to use choke, capacitor board, and filter board. Filter board is used to get rid of the electromagnetic interference, and capacitor board and choke is used to reduce it is used to reduce the harmonics level of system. And drive is what we have explained right now. For three phase, one has to use capacitor board. For single phase, you are not required to use the capacitor board, only a choke is sufficient, right? So these are the components for the drive sections in the air conditioning. With this, I'm moving to the last section of today's session, and that is on the EVI technology. Quite interesting. So let's see what this EVI technology is, which is Economized Vapor Injection Concept. Now you can see the EVI tube over here in the small sets, which is inside the compressor. Now, right? To the PH or plate heat exchanger. Now, if you see the vapor compression cycle over here, and now this is slightly modified. So this is the evaporator, the compressor, condenser, and then right? And this is the thermal expansion wall or the expansion wall. Now, after the condenser, small portion of the refrigerant is phased, right? And it is regulated through the self-solenoid valve here, and it is moved through the TXV and then a small heat exchanger or the PHE, right? So the main supply of the refrigerant is this. Remember, we have extracted small refrigerant amount through this separate circuit, and then it is allowed to move towards the through the PHE, right? Now, what happens is, since the refrigerant is allowed to move through the TXV, the pressure goes down suddenly. So you get very low pressure, low temperature refrigerant, of course, with a small amount. And the heat exchange takes place between this small amount, low pressure refrigerant, and your main line of your refrigerant, right? So here the vaporization happens, and then this small amount of vapor is injected in the intermediate cavity of your scroll, right? And then here, since the heat exchange takes place, you get the subcooling of your main refrigerant. Remember this main refrigerant line here. Since this heat exchange takes place, you get the additional subcooling of your main refrigerant line, and then it goes towards your main EXP and then evaporator, and then the vapor is injected through the suction port, right? And then this is the M and this is I portion. So you get the M plus I amount of refrigerant available in the condenser, right? So what happens is, what we are saying, of course, we'll have a detailed explanation in the next chart, is we are actually shifting close to 20% of the load from your evaporator to the PHE, right? So around 2 lakh of BTU if it is the evaporator load, you're shifting around 40,000 of BTU towards the PHE, right? So you are evaporator is freed up by 40,000 BTU and transmitted to the PHE, right? And that's how we get some additional capacity by the use of EVI. So why we use EVI? By the use of EVI, we get the additional capacity and additional COP in the system. That's the main objective of using EVI. Okay. Now let's see how it functions in a pH diagram. Now this is the pH diagram. Okay, the saturated vapor. This is the saturated liquid line and critical point. If you see the pH diagram, one is the evaporation cycle. So you can see the evaporation, the superheating, then compression happens. Mass compression here. Now I will jump to condensation. We'll try to explain 3, 4, 5 points later on. 6 is the condensation. So you can see after compression, desuperheating happens, right? Then the condensation happens, right? And then and this is the 8th one. 8 is the intermediate pressure expansion. Now, if you go back to our explanation, so we are taking up some amount of refrigerant through this expansion valve. So this is what the 8th process is. So small amount of refrigerant is expanded, right? And then the evaporation happens, and then it is injected inside the compressor via heat exchange evaporation. And then the desuperheating happens because of this your main section of your refrigerant inside the compressor, and then M plus I compression happens over here, which is called as 4 and 5. Suction plus vapor suction compressor happens inside the compressor. Right. So we talked about these points. We talked about 8th process also, but let us see 7. Now 7 is your main expansion. So main line expansion is your 7 line. So this is how. I'm sorry. 7th is the heat exchange happened inside between the small amount of refrigerant and the refrigerant. This is where we get the subcooling. So this is how your 7 process happens, which is a via heat exchange subcooling, PHE. And then it goes to the main TXT. So your pressure goes down, and then your normal evaporation. So as I said, remember as I said earlier, we have a subcooling here because of the 7th process. So you get additional EVI capacity over here because of the EVI concept. So this is where you get the additional capacity and as well as the COP overall system. So that's how the EVI helps us to gain additional capacity and additional COP system. So that's about the Economized vapor injection, and that's what I wanted to share with all of you. So we talked about refrigerant landscape, phase down schedule, the search of alternate refrigerant, then we talked about the technology, right? And then basics of variable speed and the store technology, and towards the end, just Economized vapor injection technology and how it helps to get additional capacity at system level as well as get additional CO. That's what I wanted to share with all of you. Thank you all for patiently hearing my presentation, and I hope I completed my presentation at the right time. Thank you. Over to you, sir.
Yes. Thank you very much, sir, for such a wonderful, very informative session. Now moving towards the question side.
You are not audible. You are not audible, sir.
Hello, am I audible, sir? Hello. Hello.
No. Yeah.
Rahul sir,
Rahul,
you are not audible. Please speak loudly.
Yes, sir. Hello, am I audible now, sir? Hello.
Yeah.
Hello. Yes, sir. Moving towards the question answer side. The first question is by Professor Dean. His question is: what is the percentage rise in cost of CO2 system due to high pressure operation as compared to conventional system?
Sir, I'm sorry you are not audible. Can you repeat the question, please?
Yes, sir. What is the percentage rise in the cost of CO2 system due to high pressure operation as compared to conventional system?
This need to be calculated separately because we are not from the existing design players. We are the compressor player. So one has to really calculate the percentage cost difference between existing with CO2 and system with the standard refrigerant. So one has to do some study before we calculate the percentage difference. But it is significantly high.
Yes, sir. Okay, sir. Then next question is by Dr. Tangasura. Which type of compressor is best suited to HFO refrigerant?
It depends upon refrigerant. For example, if you talk about the HFO R32, R32 is widely getting used in this cold compressor technology. Even it is also used in the rotary compressor. More than the compressor technology, I think one has to see the properties that we have seen in the radar chart and try to abide with those technologies. So I think the straight answer is one has to look into refrigerant properties, and if those properties are good enough to use, you can use in these refrigerant in any of the compressors.
Okay, sir. Thank you, sir. One more last question. It's by Professor Vijay. Is there any compressor with the help of this we can can change outlet pressure of refrigerant as per environmental condition.
That's the variable speed. That's the variable speed compressor or the inverter compressor that we say. So based on the ambient condition, we can vary the frequency of the compressor and try to deliver the exact amount of cooling capacity as per the cooling load.
Okay. Thank you so much, sir, for such a wonderful session, and it's really helped us for working with REC. So here we conclude the day 3 session day 3 session. So thank you so much, sir.
Thank you, sir. Thank you so much, and we look forward to have more interaction in future. Thank you.
Yes, sure, sir. Thank you so much, sir. Thank you.
Bye bye.